Hello learners, welcome back to the course on deformation processing of materials. In the previous lecture, we had seen the effect of temperature on metal working processes. We had seen hot working and cold working processes. And further, we saw the first metal working process, rolling. Then in that particular section, we had seen various type of rolling mills. Now, in the same metal working process, let us see some further details. So, to begin with, I'll tell you some of the defects that we can see in the rolling process. Before that, let us see something called as neutral point. Okay, so we'll see what we mean by neutral point. Neutral point. So when the rolling is done, suppose these are the rolls, and suppose from here we are putting the workpiece or feeding the workpiece, and from here we are getting the reduced product, reduced in thickness. Okay, so this, let us call this initial velocity as v naught. Okay, so I had told you that we'll call these 3 points as A, B, and C. Okay. A, B, and C points. And let us say the velocity of roll be VR. Velocity of roll as VR. Right. This is nothing but velocity of rolls. Okay. And also let us say the velocity of this product which is coming out is V2. Okay. So here this VR is given as VR is given as pi d n over 1000 meter per minute. Okay. So here d is the diameter of the roll, diameter of the roll, and n is rpm, that is revolutions per minute. Revolutions per minute. Okay, rpm. So this is the relation for velocity of rolls. Now we define the neutral point as the point where velocity of the stock or workpiece becomes equal to the velocity of rolls. Okay, so well, VR becomes equal to VS. VS. This is known as neutral point. Here we can say that this point V will be approximately the neutral point where this velocity would be VR. Okay. So how now we can define the neutral point as the point where velocity of roll is same as the velocity of stock or workpiece. Stock or workpiece. That is the metal component which is being worked upon. This point is known as neutral point. It's called the neutral point. So this is something called neutral point. Okay. Now also here there is possibility of some slipping, as there may be some uh, lack of lubrication, or not lack of lubrication, basically lack of friction that may lead to slipping of the workpiece, and there might be either forward or backward slip between the stock and the rolls. So slips are mathematically given as, so, forward and backward slips. Write it clearly. Forward and backward slips. So these are given by the percentage backward slip can be defined in terms of the roll velocity and the stock velocity or workpiece velocity. So percentage of backward slip is given as the difference between the roll and this stock velocity. Earlier in the previous lecture, we had seen that the velocity of point C will be higher than that of velocity of point B, and which will be further higher than the velocity of point A. So this is given as velocity of a roll minus velocity of the stock over velocity of the roll multiplied by 100. So this gives us the percentage of backward slip. Similarly, the percentage of forward slip will be given as now we will consider the velocity of the roll and the velocity of outcoming product, which will be V2 here. Okay. So obviously V2 is higher, so we'll take the difference as V2 minus VR over VR. Let me write it clearly. So it was V2 minus VR over VR into 100. Okay. So this gives us the percentage of forward slip during the rolling process. Okay, so this was something related to slipping. Now let us see some defects which are generally observed during the rolling operation or rolling process. Okay, so we'll now see some defects observed during roller. Okay, so let us see the first one. So basically, during rolling, what we see during rolling, there may be some distortion in the rollers due to uneven application of load, or there might be situation when the rolls are not parallel to each other with respect to, or are not parallel to the thickness of the workpiece, or we can say that they are not parallel with their axis during the rolling operation. So in that case, what happens? Let us see. Suppose this is the condition I'm talking about, like condition may arise when suppose this is my workpiece which is being rolled, and let us say this is the work roll which is in immediate contact with the sheet being rolled. Okay. This is supported by some backup rolls. Okay, so let me draw it with some other color. So let it be like this. So it's a bit tricky to draw it here. So suppose these are the backup rolls. So what happens here is you can see that the rolls are not parallel to their axis, or they have got bent to some extent. Okay, so suppose these were connected to bearing houses as we had seen earlier. So these are connected like this. Okay, so you can observe or you can see that the thickness is not uniform. Means here you can see the here you can see the thickness is say T2, and here it is T1. Okay. This is my workpiece. So here thickness is different. Due to this, what happens that the portion at the middle and at the towards the edge sides, they face a different type of loading. Okay, and if we try to see it in a different way, like if I draw it like, let us say we see it from the top, then what we will observe is this is something like this situation. Okay. This is the central part. This is the central part, and remaining two sides are the edges or side parts of the workpiece. So let us say this length is L2 and this outside length is L1. But we know that the volume will not change. Volume remains constant. So due to volume conservation, by volume conservation, we know that the width is also not going to change. So this L1 T1 will be equal to L2 T2. Okay, and we have seen that T1 is less than T2. Since T1 is less than T2, therefore obviously what will become, if we see the ratios, we will find that L1 will be higher than L2. Okay, so the material will get somewhat stretched or elongated towards the edges. It will become more longer as compared to the central part. So in that case, again, let us see what type of stresses it will feel. The, like I told you earlier, that it will become something like this. So in this situation, this central part will experience a sort of tension or tensile stress. Okay. And it will try to get stretched. While this outer side region will experience compressive loads, due to which they will try to compress, and as a result what will happen, this central portion of the material, it will try to be stretched out and keeping or compressing the sideways or the edge sides of the particular strip or sheet or the component which is being worked upon. Okay, so as a result what will happen, as a result we can say, what will happen here is the workpiece or the final finished product will become something like, it will have some waviness at the edges, and the workpiece will become something like, become distorted, like so. Let us say this was the workpiece, so it will be something like this. Okay. Some waviness will occur in the material. So now the material will appear like it is waved out from the edges. It will be stretched in the central region, but it will be somewhat sort of compressed towards the edge side. So waved edges will appear. Okay, so these are the waved edges. or edge buckles. Here, basically buckling has occurred. So this is edge buckle. This happened due to uneven stretching. Due to uneven stretching. Okay. So this is a sort of defect or problem which is observed during the rolling operation. And this can be corrected by using guide rollers. They support the workpiece from sides and prevent this sort of bending of the work roll and backup roll. Okay. Let me indicate it here also that this was my work roll, and this was the stock or workpiece stock. Okay. So to prevent it, what can be done is we can use guide rolls. Guide rolls can be used. Okay. So this was the very first problem which we have seen. Also, sometimes it may happen that this type of defect may further lead to another defect, which creates sort of stretcher marks or short cracking onto the surface of the material, and that will appear like we can say some other defect or second type of defect. It will lead to surface cracks. Definitely, you can see from this figure also that the central region will be sort of stretched out, and the edge portions will experience compressive loads, or means they will not there will not be uniform distribution of stresses, due to which there may be generation of cracks over the surface. So that will appear like suppose if there is no waviness created into the material, then it may have cracks onto the surface, some sort of cracks on the surface. Okay. Again, when the speed of rollers is not seen, means if the rolls are moving with different velocities or rotating with different velocities, and also there may be conditions when there is uneven separation, that is say from the center line of the stock or center line of the component, the rolls are separated or situated at different positions in the height. Say from the center line, h1 is the different distance of roller at the bottom, and h2 is the distance between the center line and the top roller. And if these separations become different, then in that case the material sort of gets splitted from the center line and a ligating defect is observed. Okay, so when the speed of rollers is not same, when the speed of rollers or rolls is not same, then bending problem occurs. Bending problem occurs. And if also if the separation of rules is different from the center line, then alligatoring defect is observed. Okay. So what happens in alligatoring defect is the material splits from the center and it appears like an open mouth of alligator or creature like crocodile. Okay. So this appears like, suppose this is my workpiece. So this will appear like so. This will be something like this. Okay. So here the material has opened out. This is the alligatoring defect which is observed in this particular condition. Okay. So let us see the next type of defect. So there may be conditions when the stresses are not uniformly distributed, like the one which was observed in case of this bending or distortion of rules. But there may be uneven distribution of stresses in the transverse direction or lateral direction also. So in that case, what will happen is this that will lead to either lateral spread or edge cracking. So in that case, edge will cracks due to lateral spread. Due to lateral spread. Okay, so in this case, edge will appear like it has undergone cracking. So several cracks will appear on the surface. Suppose this is my workpiece, so various cracks will appear here. So these are the edge cracks. Also, there may be some separation of the material not separation, means similar type of splitting but in the lateral direction. So that may be like this type of separation may be observed. This type of separation may be observed. This is due to lateral spread. Okay. Also, there is a situation here when suppose the rolling mill is loaded and it is being operated and functioning. Then in that case, conditions may arise, situations may arise when the rolls may also get deformed. Basically, the metal or workpiece is deformed plastically so that it can be transformed into the desired shape. But at the same time, the rolls also get loaded and they deform elastically. They don't get deformed plastically to a much extent. We will consider the elastic deformation only. So that deformation also leads to some defect in the final product, as you can clearly observe or see that when there will be elastic deformation, the desired thickness will not be achieved and some higher thickness of the component will be formed at the end. Okay, so that will be termed as mill stretch. So let us see something related to mill stretch and deformation of the rolls also. So another thing is mill stretch. Mill. Okay. So total vertical deformation will be this will be the summation of deformations of various components like deformation of rolls and the dead load, everything. Okay. So this will be deformation of rolls plus screw driven device that will be controlling the rolls plus the housing. Entire thing will contribute to this deformation, vertical deformation of the rolling system or rolling mill. Okay, so suppose if my rolls were like circular in shape, then during working, they may get deformed to some shape like this. Okay. So there is a term known as mill stretch, and it is given in terms of the mill modulus. Okay, so there is a plot between the rolling force, roll force, okay, and the mill stretch. So this particular graph goes like Let me draw with some other color. This graph goes like something like this. Okay. So this is the initial deformation due to the dead load. So there is a relation also to correlate this with the mill modulus. So suppose if F is the rolling force and this vertical deformation, if we say it is measured in mm, so this will be force per millimeter, and suppose this initial deformation is S naught, then this summation will be equal to the mill modulus. Okay, and its unit will be unit of force per mm, like mega Newton per mm or Newton per mm or tons per mm. So this is the relation. Here, this particular term is rolling force by vertical deformation. So this is rolling force by vertical deformation. Or mill stretch. This is the mill stretch itself. Or mill stretch. This was the initial deformation. Initial deformation. This term came due to the dead load. Okay. So this is something about the mill stretch. Basically, mill stretch comes into picture when the rolls are working or they are doing their job of deforming the metal. They themselves get deformed, and that particular thing is defined in terms of mill stretch. This initial deformation is the total deformation due to the dead load, means when the machine is not functioning and it is loaded by its on load only. Okay, so don't get confused in between these two. So this was something related to the defects. Now let us see some of the parameters or mathematical things which can be controlled or which affect the rolling process. Okay, so we'll see some of them. So we will see projected length, we will see the maximum draft. Maximum draft will be the maximum reduction possible in the workpiece cross section. Draft, we had seen that it is the difference of initial and final thickness, that is the reduction in the thickness. So what is the maximum value which can be achieved? Projected length, we'll see in a while what it is and how is it calculated. Then we will see uh, the value or correlation of bite angle with the draft and roll radius. Okay, so let me draw the schematic first so that we can easily derive the parameters. So suppose, let me take some shape. It is much better. And if I copy it, it's a bit difficult to draw it here. Okay. So suppose this is another row. Okay, and these are aligned with each other. Suppose this is a workpiece which is being deformed. Okay. This is the product we are getting. Let us call these particular points. See here, this particular angle will be the bite angle. Okay. So suppose if this is alpha, so if this angle is it's a alpha, and this distance is, let us say, x. Let me call these points as A, B, C, and D. So if this is A, this is A, this is B, this is D, and this particular point is B, let us say. Also, so there will be forces acting here. Here there will be normal force acting. Okay, and there will be frictional force in this direction. So this is a normal, and we know that if we know the normal, then if we multiply it with the coefficient of friction, we get the frictional force. So in this direction, frictional force will be acting. And suppose if the initial thickness was T1, this is T1, and the final thickness is T2. Okay. So we will derive everything based on this particular schematic only. Okay. So suppose my rolling operation is being done, then in that case, the projected length is nothing but this particular uh, distance AB. So like this is the portion So this particular distance AB. AB is defined as the projected length. This is the projected length. Okay. Now we know that the draft is nothing but the difference in the thickness. So T1 minus T2. Okay. So this is the draft which will be observed in this case. And alpha we have defined, this is the bite angle. Okay. So alpha is the bite angle. Okay. Now let us see the projected length. How is it calculated? AB we have to calculate now. Okay. So from this figure we can say that BC is the radius of the roll, which is nothing but R, capital R. Let me write it here also, that the radius is R. Okay. Now in this case, BC is equal to R, which can be seen from the figure. BD is the half of the draft. Half of the draft is at the lower roller or bottom roller, and half is at the this particular section that we are seeing, the top one. Okay, so BD will be D by 2, and also AB we have to find, which is nothing but the projected length. Let us call this as L. Okay. Now let us apply simple geometry. So we will first consider the triangle ACD or ADC. So in triangle ADC, applying the Pythagoras theorem, what we can write is the square of AC will be equal to AD square plus DC square. Okay, so AC square will be equal to AD square plus DC square. And we have seen that AD is written as X here. Okay, and BC will be nothing but BC minus BD. Okay, so BD we have written that it is D by 2. So AC is nothing but the radius R. So R square. Okay, and AD we have seen it is X. So it is X square, and DC is nothing but the radius minus DC is BC, which is radius minus BD, which is D by 2. So D by 2 square. Okay. So solving this or rearranging this, we get R square is nothing but X square plus R square plus D square by 4 minus 2 R B by 2. Simple mathematics. Okay. So let us rearrange the equation. So this R square term gets cancelled, and this also gets cancelled. So ultimately we are left with this X square as RD minus D square over 4. So this X is nothing but square root of RD minus D square by 4. Okay. This was the case of triangle ADC here. Now we have to find AB. So let us now consider the triangle ADB. In triangle ADB, again applying the Pythagoras theorem, AB will be equal to, means AB square is AD square plus BD square. So AB square is AD square plus BD square. Let us substitute the values. So AB we have to find, this is L square, and AD is x square, means AD square is x square, and BD is nothing but d by 2 square. Okay. So if we put the values back, this L square is x square, we know that it is RD minus d square by 4. This is again d square by 4. These two terms get cancelled out. So ultimately this L square becomes RD. Now we have found the projected length. It can be more clearly or written in a better way as this. Okay. So this is the projected length. Okay. So this was the first parameter. Now let us find the relation between the bite angle, the draft, and the roll radius. Okay. So let us see the next parameter. From this particular figure, we can say that tan alpha will be equal to AD over DC, and AD is x. DC we have written it as this radius r minus half of the draft. So from here, tan alpha is AD over DC, which is nothing but x over r minus d by 2. Okay. So this is given as under root of RD minus d square by 4 divided by r minus d by 2. Okay. Now, since this draft is very less, it is actually very less than 1, because we do not reduce the thickness to a very great extent in a single pass. Okay, so in that case, what we can say is, since d is very less than 1, so definitely lower terms can be, or higher order terms can be ignored or can be neglected. So in that case, this d square by 4 becomes very less, so as it can be considered to be negligible. Also same goes for d by 2. So these are negligible. Okay. So what we can say is, this tan alpha becomes under root of r d by r, or more simply, tan alpha can be written as under root of d by r. Okay. So this is the relation between this bite angle alpha, draft d, and roll radius r. Okay. So let us say this was the first relation, this is the second one. Now let us see the maximum draft which can be achieved during this rolling operation. Okay. So for better clarification, Let me draw this particular loading condition again. Okay. We will see only the loads which are acting. So at the point C, the angle is alpha. Okay. So let us see how it appears. So this is the vertical direction. Suppose this was the loading direction. So this angle was alpha. Since this is alpha, this angle becomes 90 minus alpha. 90 minus alpha. And again, the loads which were acting here were the normal reaction. I'm only indicating the direction, actually not at the particular point. Means the load acts in this particular direction. Okay, so let us say this at this point itself. This is the point of contact of rolls and the workpiece. So it is like this. So definitely the frictional force will be like this. If this was n, this was mu n. So let us resolve the components and let us see what is the load in horizontal direction. So we will see what is the load required for taking in the workpiece, beyond which or below which it will get slipped. So this angle is 90 minus alpha. Again, this will be with the vertical, it will be alpha. This will be again alpha. So if we resolve the components of these loads, we will see for this n, the components are this will be n cos alpha, and in this direction there will be n sin alpha. Okay. And similarly for this mu n, let me draw it a little further. So say this was mu n. So in this case, since this is 90 minus alpha, so again since this is 90 minus alpha, so again this will be alpha. Okay. So again the loads will be in this direction. We will get mu n cos alpha and here we will get mu n sin alpha. So if we consider the loads in horizontal direction, we can take into account the slipping factor or minimum, or sorry, the value of load required for the material to pull the stock towards the rolls so that it can get deformed. Okay, so what happens here is Rx, suppose it is the reaction load or load in this x direction, will be mu n cos alpha minus n sin alpha. We can see from the resolution of loads. Okay. And with to take the material without slipping into the rolling system or rolling this setup, this Rx should be greater than or equal to 0, because if it is less than 0, so total reaction force or resultant will be in the left direction here, and the material will get slipped. It will not be pulled. Okay. So rearranging these equations, minimum value should be 0 here. So in that case, we can say that mu n cos alpha should be greater than equal to n sin alpha. If we neglect the greater than, then we can say that mu n cos alpha is n sin alpha. This will be the critical value. This is the critical value. This n will get cancelled out, and this mu will again become sine, and this cos will become and come into denominator. So this will be tan alpha. This is for the critical value, and tan alpha we have seen that it is nothing but under root d by r. D by r, where d is the drop. Okay. And since it is the critical one, so this mu is nothing but maximum drop over roll radius square root. Okay. And again rearranging, we can say that this is mu square is d max by r, or simply the maximum drop is nothing but mu square r. This is something related to the rolling operation. These were some important parameters which we have seen. Okay. So now we will end for today. We'll close the session, and in the next class we will try to finish the rolling process and start the next one. Okay. So thank you everyone.